Welcome to Chapter 10, Section 3. This is our last section, and we're going to be talking about the second law of thermodynamics. So the things that we're going to cover today is we're going to recognize why the second law of thermodynamics requires two bodies at different temperatures for work to be done. We're going to calculate the efficiency of a heat engine, and we're going to relate the disorder of a system to its ability to do work or transfer energy as heat. So the second law of thermodynamics tells us that no engine can perfectly convert all the energy from heat source into work. So we talked about cyclic processes last time, and we had that example of a heat engine. And remember, we talked about how we had our cup, right, with our heat engine on top, and it had the little blade that spun, right? But we could feel the heat radiating off the cup that wasn't going into the work to spin this blade around. Okay, so that tells us that not all the heat is transferred perfectly into the work. Okay, so we lose some of it to the environment. So what this looks like mathematically then is our net work, remember, is equal to the heat from the heat source minus the heat lost to the environment. And so what this law tells us is that our QC cannot be zero. So no cyclic process that converts heat entirely into work is possible. There's no way for QC to be zero. Okay, so it can't be zero, so QC must be greater than zero. However, we can talk about how some cyclic processes convert more heat into work than others. So different heat engines, different cyclic processes some of them will take more of that heat and turn it into work, and others of them will take less heat and turn it into work, and more heat will be lost to the environment. So what we say when we're describing this is we say an engine is more efficient if it converts more heat into work. And when we're doing this in an equation here in a minute, we're going to use EFF for efficiency. So we can also say that efficiency is a measure of the useful amount of energy taken out of a process relative to the total energy put into the process. And I want to highlight that useful amount of energy. So let's take a look now at an equation and how we might figure this out. So our equation for efficiency starts out as EFF equals the net work done, that's our useful energy, divided by the total energy available to do work, okay, or our energy coming from the hotter part of the system. We can also write this equation, if we remember, net work equals QH minus QC. So we can actually rewrite our equation here now as QH minus QC divided by QH, which will simplify then into 1 minus QC divided by QH, or 1 minus the energy lost to the environment divided by the total energy in the system. So these are two different ways then that we can calculate the efficiency of a heat engine. So let's do an example now. So we've got an experimental gasoline engine, okay, and it does 45 joules worth of work and gives up 31 joules as heat to the environment. So what is the engine's efficiency? All right, so we know we've got our equation for efficiency is EFF equals net work divided by QH. So now we've got to identify what in our problem here, what information we have. So it says it does 45 joules of work. So that means our net work must be 45 joules. Okay. And it gives up 31 joules as heat to the environment. So because that's heat to the environment, that makes it our QC. So our QC equals 31 joules. Okay. Now, but our equation here, though, has QH, so we got to find QH. So we need to remember that net work equals QH minus QC. And so we can plug this in, 45 joules equals QH minus 31 joules. So our QH will be 76 joules. And now we can plug that into our equation. So our efficiency will be equal to our net work of 45 joules divided by our heat available to do work, which is 76 joules. And when we plug that into a calculator, we will find that we get 0.59 is our efficiency. So what does this mean? Well, an engine that converts all the heat available into work would have an efficiency of 1. And we have an efficiency of 0.59. So often it's easier to think of this as 59% efficiency. Okay. Makes it make more sense to us more easily by putting it in percent. But your book uses just the decimal form here, like 0.59. Just remember, you can easily convert that to efficiency. And just to take this one step further in connecting this idea, if you talk about the typical gasoline engine, like in your car, that is actually only maybe 25% efficient for the typical gasoline engine, and diesel engines tend to run at 35% efficiency. So as you can see, a 59% engine would be pretty good. Moving on now, I want you to start thinking about a deck of cards, because we're taking the second law of thermodynamics a little bit further now. Okay, and if you think about a deck of cards, right, you have the ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Okay, and how many ways could we align them and order them from ace to king correctly and by each suit, right? Well, you'd have, the hearts lined up, and then you'd have the diamonds all lined up, and then you'd have the spades lined up, right? And then the last one is the clubs all lined up, right? But really, if you line all those up in order, there's only one way to line them all up in order. And we would say it's very organized this way. Okay. So then, now if we look at this another way, so think now about what happens if you shuffle your cards. So we're going to mix them all up. How often, if we're just shuffling them randomly, how often will the cards all line up in that way we just talked about? Okay. Well, card decks have 52 cards. Okay. And it turns out that it's very unlikely for those cards to just on their own, if you're shuffling them randomly, end up all in the correct order. Because those cards can be arranged so many different ways, right? We could have 2, 3, 4, 5, and then 1, or we could just have them all mixed up. So we'd actually have to count all the possible ways to organize cards, and all the ways to organize cards, all the different possible ways they can be arranged, ends up being 8 times 10 to the 67th. So 67 zeros. That is a huge number. Okay. So how often will the cards all line up that way? Well, it will happen once, because there's one way to line them up, divided by that 8 times 10 to the 67th. So that ends up being an extremely small number. So what this tells us is that there are more ways to be disorganized than there are ways to be organized. And it turns out this isn't true just for decks of cards. It's true for everything in life. You can think about cooking or cleaning your house at home, right? There's only one way for all your books and all your things and all your clothes to all be put away. But there's a million ways that those could be thrown all about your room or all about your house where they don't belong. So there's always, always, always more ways to be disorganized than there are ways to be organized. And that leads us to this thing called entropy. Okay. Entropy is the measure of randomness or disorder of a system. Okay. So it's a way to essentially count how disorganized something is. And we're not going to actually do any equations with this, but I still want you guys to see the idea. Okay, so basically if something is disorganized, we'd say the entropy of a system is big if it's disorganized. And we would say that entropy is small when things are organized. So we can also look at the entropy of particles in matter. So the more disorganized the particles are, the more entropy they have. And conversely, the more organized the particles are, the less entropy they have. So let's look at an example, and this is one from your book. If we had all these particles and they all happened to be going the same direction, okay, then it would be considered very highly efficient because all the particles could hit this thing and do work on it. Okay, but it's very, very, very unlikely that this system would actually happen in nature because really particles are always bouncing all these different directions, like these ones over here, going this way and that way and this way and that way, and all the different directions. Okay, so the average efficiency is much lower, okay, but it's much more likely to happen. So we would say that this side of things has a very low entropy because it's very organized, and this side would have a very high entropy because it's very disorganized. So then when we connect this idea to work, okay, highly organized systems can convert more energy into work, but disorganized systems can convert less energy to work. And again, just think about it as moving this little thing here. If they're all going the same direction, it'll be really easy to move that. But if they're all bouncing all over, only a few of the balls will hit this with enough force to cause it to move. So only a little bit of work will get done. Okay. So what this tells us is that actually entropy is another way to express or tell us about the second law of thermodynamics. And this is because, remember, when we talked about the second law originally, we said that not all the energy available will be converted into work. Okay, so with that too, if you think about those random motion of particles, not all the energy in a system is even available to do work, because if the work is this direction, some particles are moving that direction. Okay, so not all energy in a system is available to do work due to the random motion of these particles. So you might be thinking about this and be thinking about like, well, but we still like put all our stuff away, we still organize things, we clean them. And there are a lot of places on Earth where entropy is reduced, okay, where entropy gets less. So things like biological systems, like our bodies, plants, animals, all these things take random atoms, they put them together into molecules, okay. Molecules have a lower entropy than random atoms by themselves because they're more organized. Okay, also humans, we take disordered things like all these big chunks of metal and we shape them and put them together into useful machines. So these are examples of where we're reducing entropy. Okay, so that seems to kind of contradict the second law a little bit. But let's look at an example and I'll show you how it doesn't contradict. Okay, so this is from your book and I thought it was a really good example. Because when you put things in a freezer, okay, what you happen is you take all these random water molecules, right? And they're all moving about and they're disorganized. And when you freeze things and turn it into a solid, solids have this definite structure and you can see the pattern here, right? So what we've done is we've reduced the entropy. Okay, so if we go this way, we reduced entropy. Okay. But what happens is even though this is a small decrease in entropy, what's happening in a refrigerator is you have all these elements here on the back side. And what they do is you actually have heat that is given off. So your refrigerator gives off heat, okay, and that's in proportion to the entropy lost. But actually what happens is that increases the entropy a lot. So you notice here it says small decrease, and here we get a large increase. So it takes the air around the refrigerator and the particles are moving a little bit, and then as it freezes things and cools them, those particles end up zooming around a whole lot. So this increase in entropy here that's happening outside the refrigerator is actually more than the decrease in entropy we get for the things inside. And that's really important that this is bigger than this, because that follows our second law of thermodynamics, because not all the work we do, okay, to decrease the entropy, some of it goes into increasing the entropy of the air. So with this too, if you think about it, you could never leave your refrigerator door open to cool your house. Because yes, it's cooling things in this space, but as it does so, it does a lot of work back here and gives off heat. And the heat it gives off here is more than the cool air produced here. Okay? So a refrigerator could never be used to cool your house. So that brings us then to the end of Chapter 10 and the end of thermodynamics. Let me know if you have any questions, and I'll see you guys in class.